Okay, welcome back. Yeah, so as I was saying, now the focus of this second part onwards is more about this data-driven stochastic optimization, where again, you're trying to solve your stochastic optimization problem, but the distributions are now unknown. You only have access to some kind of data, historical data. And I mean, I'll talk about like what does data mean in different contexts, uh, at least a few modeling assumptions. Good. So first of all, again, just to recap, stochastic optimization, I'm thinking of usually independent distributions and distributions, some constraints. You want to find some kind of an algorithmic solution to maximize or minimize your objective value in expectation. Good. And we talked about like a bunch of these problems like revenue maximization, auction design, optimal stopping. So generalizations called resource allocation, Pandora's box. There are many other problems. Good. And the point is, what if the distributions are unknown? Good. So, so we need usually some kind of access to distributions. So here's another extreme model that one could take is that there is no underlying distributions. The inputs are fully adversarial. And there are problems, algorithmic problems, where even for fully adversarial arrivals, you can hope to design algorithms which have some performance. But as you may guess, for most problems, these bounds are very pessimistic. Like they'll show you, like at best, maybe they can show you some logarithmic approximation, like or like a log n approximation, or they'll show you something like a factor n approximation, which is usually very bad. So that's why for most problems, it makes sense to assume that there is an underlying distribution. So when I say we want to do these stochastic optimization problems, I want to do this for an underlying distribution. What's unknown is that the distributions are unknown, but there is an underlying distribution. So in some sense, what modeling assumption we have made here is that there is a hidden distribution underneath, just that I don't know it. So, but there exists a distribution. It's not an adversarial input. It's a input from some underlying, potentially a worst case distribution. Good. And the access that we have to this distribution is via some kind of historical data. So, okay, what do I mean by data? So one of the most natural ways is as some kind of offline learning, which literally means I give you a bunch of samples, like independent IID samples from the underlying distribution. And your goal is to come up with an algorithm or a solution, potential solution, and whose performance will be measured on like a freshly drawn sample from the underlying distribution. So I'm going to give you a bunch of training samples, use the training data to come up with some solution. For instance, like even going back to like, it's the same thing like machine learning classifier or something. You want to use the historical data, come up with a classification, like say a linear classifier, and then I'm going to evaluate its performance. You can say a similar thing even for problems like say revenue maximization. Use your historical data to come up with a price P, and then I'm going to use this at this price. What's the expected value of your algorithm? Does this make sense? Like, so the example here is like you want to maximize say, the revenue maximization. You want to come up with a price to maximize this thing. So you have a bunch of samples from the underlying distribution. And this model can be like used to talk about like optimal stopping problem, where maybe your algorithm comes up using the historical data. It comes up with some kind of thresholds, when to stop, like when to take the next random variable. Similarly, for Pandora's box, it maybe comes up with some kind of indices or something based on the historical data, and then you run some kind of a policy on that. How well does it perform? Another thing could be, so most of the focus today will be offline learning. And but another thing that's very commonly done is online learning. We'll talk more about it like in the next lecture, like lecture 3, 4. Here, basically, in some sense, you start off with no data. It's a repeated kind of a game where in each round, you play an algorithmic solution. And then you get some kind of a feedback on how well it performs. Then you repeat again, play another algorithm, and you get another feedback. So for instance, like in going back to this revenue maximization example, like the carrot is offered at some price to the bunny today. You get some feedback whether the carrot sold or not. The next day, you again offer the carrot to another bunny drawn from the underlying distribution. Again, you get a feedback whether the carrot is sold or not. So this is the so-called online learning framework where you're learning as you go, and your objective is to perform well on average. on average over T rounds. Let's say maybe on average over the year, I'm going to do it like 365 times, 365 days. Each round I play like a fresh, another algorithm. So that's what's called online learning. And your goal is to perform well on average. And you could be receiving like some kind of feedback, maybe some kind of a full feedback. A full feedback would basically mean at the end of each day, I'm going to see exactly how much the value the bunny had. Like, so this gives me more information in the sense I knew that maybe bunny's value was much higher. So I should be offering him or her like higher prices in the future. Partial feedback would be something like I only learn whether whether the carrot got sold or not. So there are like many variants of these things, and we'll talk about this later. Today's focus is just upon the classical offline learning model. I give you a bunch of samples, use these samples to come up with an algorithm which has a good performance in expectation. Any questions? Okay, good. So again, to recap, like what's the setup? I'm going to give you a bunch of, like I'm calling capital T samples. One thing to be careful about is what do I mean by a sample here? These are n distributions. So by a sample, I would actually mean an n-dimensional vector. So by a single sample, in some sense, I'm giving you not just a single scalar, I'm giving you x1, x2, x3, xn. So the superscript t here denotes the tth sample. So tth samples, first coordinate, second coordinate, third coordinate, because these were, remember, n distribution. So a sample here means like an n-dimensional distribution. So a sample from this n-dimensional vector. So the setup is I'm giving you capital T such samples upfront. Based on these samples, your goal is to come up with some algorithmic solution whose performance is basically the expected value drawn from a freshly drawn sample X from this underlying distribution. Good. And optimum is basically amongst your every possible algorithm. Like basically, ideally, you want to compare yourself to this underlying MDP. Had I known the distribution, there's this exponential sized MDP, whatever is the optimal solution to that MDP, that's my kind of benchmark. So how will I compare to, like how well do I perform compared to that benchmark? And there are variants of this problem as well, where you maybe sometimes don't compare to the entire class of algorithms, solutions, but like just compare yourself to a restricted class of policies. But let's say we are comparing to the entire class. And the usual objective, so there are two usual objectives. One is the regret, which is the difference in the performance of your algorithm compared to the performance of the optimum. The other is the ratio, the competitive ratio, or the approximation ratio. Today, at least, or for the first 2 days, we'll mostly focus on the regret version. For most of these learning problems, turns out usually regret is the best you can hope for. Usually, like approximation ratio results are usually not possible. In the extreme case, like if the underlying, like, so one reason, for instance, like a multiplicative guarantee is usually not possible is like things like, suppose there's an underlying distribution which takes like a very high value with an exponentially small probability. So suppose you have a random variable which takes like a trillion value with 1/1 billion probability. Now, unless you receive like a billion samples, there's no hope to like getting even like a mean of the distribution. So this is one of the reasons why approximation ratio or competitive ratio, which is usually scale invariant, you cannot hope to get some kind of these multiplicative guarantees. You can only hope to get some regret additive guarantees where you basically bound the range of the random variables. Maybe all random variables are between 0 to 1, and I can get you an additive epsilon approximation. So yeah, again, but competitive ratio is still possible for some specific problems because there's more happening in the problem because depending on the structure of the problem. But for most learning problems, regret is the right framework. And so that's what we'll focus on today. Again, like if I confuse you, like at a high level, the main question today will be, given a bunch of samples, like or in some particular, what is the minimum number of samples I need so that I can learn an algorithm which is additively off from the optimum by at most epsilon. Does this make sense? Yeah, I think I messed up slightly. Like it should be f of opt minus f of alg because it's a maximization problem, but I guess, yeah. Good. And the example, like for instance, like in revenue maximization problem that we talked about, What's the minimum number of samples I need to give you so that you maximize the revenue up to an additive epsilon. This additive epsilon, again, like to say it again explicitly, additive epsilon only makes sense if you have some scale of the problem. Like if I scale every number in your underlying problem by a factor 100, then in some sense the regret will also scale by a factor 100. So this only makes sense if there's an underlying scale. And the scale we'll kind of assume is that all, like the function's value will always be between 0 and 1. If it's like between 0 and k, usually it will become like epsilon times k in some sense. So there's an underlying implicit scale of the problem. So the question is, for like say revenue maximization, optimal stopping, again, like you have these random variables, you want to decide when to stop to maximize the value. You might be playing some kind of thresholds when to stop. And the goal is to come up with a solution which has additive epsilon guarantee, similarly for Pandora's box. Is the objective clear? Okay, good. So maybe a few more comments on the model in particular compared to other models. So first of all, this is pretty much the same as the PAC model and like the standard learning theoretic model. It also goes under the name of agnostic learning sometimes. Yeah. So it captures also online learning with full feedback. So this model of online sequential learning, I'll comment on this like maybe like in the next lecture when we talk about online learning more, but online learning with full feedback and this model are basically pretty much the same. One reason is maybe usually the doubling trick. I can use the first few samples, like first 100 samples to come up with a policy for the next 100 rounds, and then use the first 200 samples to come up with the next 200 rounds. And by losing like especially up to a log factor, they're basically all the same models. So it doesn't make too much of a difference. There's also a lot of work on learning for specific classes of distributions, like maybe for Gaussian distributions, like what can I come up with? Can I come up with a good algorithm? Or like for exponential class of distributions. So for specific classes of distributions, one could hope to do better. In this like talk, we'll be talking about like general learning. I won't assume anything about the distribution, besides the fact like my functions are between 0 to 1. Beyond that, we'll talk about general distributions. And as I had commented earlier, like, okay, one could also talk about competitive ratios and approximation ratios. That's usually not possible, but for some specific problems, like we'll talk about some online resource allocation problem on the final day, where even multiplicative guarantees are possible. Good. So for the next half an hour or so, the plan is basically we'll talk about some simple bounds, some simple techniques, how we can obtain some guarantees. So recall, like our main question is, what's the minimum number of samples capital T that I need so that I can learn the optimum solution up to an additive epsilon. Good. Okay. So first class of algorithms we want to study is, let's say, if I'm given somehow that the class of candidate algorithms is relatively small. Usually like the number of algorithms is finite. So either imagine that somehow we are given upfront that the class of potential algorithms to consider is small, or sometimes what happens is the class of algorithms might be infinite, but you can discretize the problem and then assume that the potential algorithms is only relatively small. Good. So for instance, in the revenue maximization problems, what's an algorithm? An algorithm is basically setting a price between 0 to 1, at the price at which the carrot is to be sold to the bunny. A priori, the number of algorithms is infinite because there are infinitely many possible prices between 0 and 1. A finite class of algorithms would be maybe I only want to play prices which are multiples of epsilon for some appropriately chosen epsilon. So that would be like a discrete class of algorithms. So I'm thinking of problems where the number of algorithms is finite. The reason, as we'll see, like the sample complexity bounds we'll get will depend logarithmically on the number of potential algorithms. So as long as you are in a setting where you're fine with a logarithmic factor loss in the number of algorithms, simple things can be done. So what's happening is that, okay, so suppose the class of algorithms is finite. Capital A is what I'm calling the class of algorithms, and all values are between 0 and 1. Then one could do a very simple thing, just the Chernoff bounds. So the claim is that you can get a regret up to an additive epsilon with probability 1 minus epsilon. as long as the number of samples is something like 1 over epsilon squared times log of the number of algorithms and times like 1 over delta. Does this make sense? So usually like for any of these problems, like you have to lose at least a 1 over epsilon squared factor. So simple reason maybe like the classical example, like even if I give you like say a single coin, whose mean is some constant between 0 and 1, you need at least something like 1 over epsilon squared samples to learn the mean of this random variable up to plus minus epsilon. So if I give you a coin whose, like say, P is like probability of heads is like say some between 0.3 and 0.7, you don't know where, you need at least 1 over epsilon squared samples to calculate the mean. So that's the underlying intuition why pretty much in all of these problems, you have to lose at least 1 over epsilon squared. It's the same reason why like if you do n coin tosses from unbiased coin even, you get n over 2 plus minus square root n. So this plus minus square root n, you kind of have to lose. It's the same, the standard deviation. So that's the same reason this 1 over epsilon squared you have to lose. And you lose a logarithmic in the number of class of algorithms. And this delta parameter is the error parameter. Good. And the proof of this is literally just Chernoff bounds. So what we could do is look at any particular algorithm in the class. What's the chance that this algorithm's performance on your samples is epsilon, like after capital T samples, like there's some expected value of this algorithm times capital T. That's what you would have expected the sum to be. This plus epsilon T or minus epsilon T, this happens with precisely like given by the Chernoff bound, which is bounded by e to the minus epsilon squared T. So if you choose T to be as given here and take a union bound over all algorithms, you'll basically get with 1 minus delta probability, I've learned everything. Question?
Here, so that top is in the A, right? Because if it's not,
yeah,
also have some.
Yeah. So that's the like about this first line of assumption. Maybe it was not written very clearly. Yeah, algorithms belong to that. Basically meant opt is in the benchmark is in this class. Yeah, precisely. Good. So I mean, I've not done anything fancy, but what I'm basically saying is that if the class of algorithms is small, or actually it need not be super small. I mean, you can even it could be somewhat exponential because we'll be only losing logarithmic in the number of algorithms. So simple Chernoff bound will already give us a reasonable guarantee. Does this make sense? And like again, like maybe say going back to our revenue maximization problem. So remember, we're trying to find a price to maximize like the expected revenue and to sell a carrot to a bunny. So a priori, the number of prices are infinite. But it turns out you can only consider prices as multiples of epsilon. Because if I change my price by additive plus minus epsilon, like you can argue that, okay, the optimal loss in revenue is only like up to an epsilon. It's not more. So like whatever is the optimum price, if I scale it slightly down, or so you can argue that I'm going to lose only like at most an epsilon. And so now the number of potential algorithms is only like 1 over epsilon. I just put it here. So you get some like 1 over epsilon squared times some log 1 over epsilon kind of sample complexity. Good. So this is a problem where although the number of potential algorithms was infinite, simply by discretization, I was in a good shape. Any questions? And the same trick can actually be applied, like not just in single dimension, even in higher dimensions, often this works. So even if you're in higher dimension, discretization often works, not always, for many problems it does. So the approach here is like this is a generic kind of an approach. So step one of this algorithmic approach would be argue that if I change my distributions from 0 to 1 to say some multiples of epsilon prime from 0 to, okay, this is a typo. This should be 1. I mean, I'm not changing. Yeah, the range is still like, 0 to 1. So epsilon prime, 2 epsilon prime, 3 epsilon prime. So 1 over epsilon prime times epsilon prime, which is 1. So argue somehow that this only hurts your optimum by not too much. Like say if you're in an n-dimensional space, maybe it hurts your optimum by only like a factor n epsilon prime. This does not hold true for all stochastic problems, but for many problems it does. And then separately argue that we need to now consider only algorithms who are also playing some thresholds or policies, which are scaling something like, okay, another typo. This should be 1 over epsilon prime to the power n. Yeah, so this should be 1 over epsilon prime to the power n. So as long as the number of algorithms is only scaling something like singly exponential, if the number of algorithms is this, then I can just substitute in like the bound from the last slide, which was like 1 over epsilon squared times log number of algorithms over delta. If number of algorithms is only like 1 over epsilon prime to the n, then you get some guarantees. So you can already start getting n over epsilon squared kind of sample complexity if you're in n-dimensional space using this simple discretization trick. And to give again examples, like this is one of the exercises, is that to formally prove that actually this can be applied to problems like optimal stopping and Pandora's box. So both these problems, you can actually apply this discretization trick, and it already gives you a good sample complexity. Need not be optimal, but it's pretty good. So it turns out, for instance, for optimal stopping, you can actually shave off this n. You can only need to get like a 1 over epsilon squared. So you can actually do better using alternate techniques, but this gives you like already a pretty reasonable one. So actually in this tutorial, I'll mostly focus on the sample complexity bound as a function of epsilon. So 1 over epsilon squared, like I aim to get that tight, but yeah, but sometimes, yeah, that's not possible. Good, but there are problems where this is not always possible. So what are some of the limitations of this approach, this discretization approach? The first limitation is there are problems where you cannot just discretize. So it turns out problems like auction design for multiple buyers. It's known that discretization cannot be done, like involving multiple buyers and items. Discretization, if you try to discretize, it no longer preserves truthfulness, like whatever truthfulness means, like or basically incentive compatibility, because then people have like incentive to deviate, like reporting in non-truthfully. So there are stochastic problems for which discretization is not a possible move. But I mean, I think that's still, I mean, discretization, this trick does work for a very large class of problems. So in that sense, it's still interesting. A bigger flaw to me is the second point, which is that this is usually not a polytime. So what do I mean by this? So what we basically showed here is that I give you a bunch of samples. Now for all these samples, the approach I'm suggesting right now is check out every possible algorithm, see what is the performance of that algorithm, and take the best of these algorithms, also known as empirical risk minimization. But now the class of algorithms is potentially exponential, like something like 1 over epsilon to the n. I cannot hope to try all of these algorithms in polynomial time. So in general, this approach, it's not clear how you would go about solving it. Like ideally, what we would have liked is that suppose I give you a stochastic optimization problem, which if I knew the distributions upfront, I have a black box to solve this problem. Like all these techniques that we saw in the last, like the first part of the lecture, the approaches based on linear programming, dynamic programming, Gittins index, any of these things, they are tailored to product distributions, like something about the distributions. So ideally, I want to say like, if I have a way of solving a stochastic optimization problems, given the distributions, like if I had known the product distribution, then I can solve it. Then can I learn it as well? So ideally, I wanted to use that as a black box. What has happened here is that I've obtained all these samples. Now, these samples are not like product distributions. These are like literally n-dimensional samples. I cannot feed these samples. I mean, they don't give me a product distribution. And hence, I cannot feed those samples into a black box to solve the problem. So this is the reason why this approach is not polynomial time. Okay, this is somewhat subtle, so maybe let me take questions. It didn't make sense. Yeah.
The approach is where you know the full distributions, you don't use everything about the distribution, right? Maybe you could still give what you need. So.
Yeah, exactly. So there could be problems where, yeah, I mean, so okay, let me say, I guess the point is, the subroutine that this problem is giving you is, I've given you a bunch of samples, n-dimensional samples. If you can find the optimal algorithm, basically solve the empirical risk minimization problem, then this is already a very good solution. So if that is possible, then it's good. But for a lot of the problems that we discussed earlier, like or high dimensional revenue maximization, optimal shopping, and a lot of these other problems, turns out if I give you arbitrary empirical risk minimization, you cannot relate. So these are hard problems because they lose the product nature, because now each sample is an n-dimensional sample. So in some sense, it's an arbitrary n-dimensional distribution. You have samples from that rather than a product distribution. So hence you cannot, like, often not solve with the empirical risk minimization problem. There could be stochastic optimization problems where you could solve that. And then this is a very nice approach. But so what we would aim for is something like the following, that so maybe to comment a bit more on this, an alternative would have been something like you have these samples. From each of these samples, like the T samples that I have, I construct some kind of a product distribution out of it and use that product distribution as input to my black box oracle and run that as an algorithm. So maybe this will become clear later on. But yeah, what I'm saying is that this discretization trick works. It works quite well in the sense of it gives you some sample complexity bounds, at least to get you started. It may not be optimal, but at least it gives you some bounds. One of the biggest drawbacks is for many stochastic optimization problems, especially the ones that we talked about, like all these auction design problems and so on. Turns out these problems are provably hard for general distributions. It's only for product distributions that they have good structure and you can actually solve them. Hence, the empirical risk minimization problem cannot be really done, because that involves like arbitrary n-dimensional distributions, like samples from there. So you cannot solve that optimally or efficiently. Instead, what you can do is, like, or hope to do is, use these samples to construct a product distribution and send that product distribution to your black box and use that as an algorithm. So that's the hope. Did that make sense? Okay, maybe it will become clear like after some examples. Good. So like the point I want to make is like somehow we want to exploit that the distributions are independent. Okay, but if you can solve the empirical risk minimization problem, then in some sense, this is already a pretty good bound for many of these problems. Okay, so the next approach that we want to take, like say in the next 10, 15 minutes, is how to handle discrete distributions. So by discrete distribution, I basically mean here that the support size of each distribution is at most. So let's say like for some reason, the random variables were already given to be like multiples of epsilon. So you don't have to discretize them. So they're all like 0, epsilon, 2 epsilon, 3 epsilon, something like that, multiples of epsilon. And k basically in that case would be 1 over epsilon. But it could be more general distributions. So in this setting, as we'll soon see, you can already get like pretty good. Okay, a quick question. How many of you have seen like TV distance or coupling before? Have you heard of these things? Okay, not coupling. Okay, good. So yeah, so we'll go again slow. Yeah, good. So here's the plan. So you have these, remember, n distributions. Think of like any of our problems, like Pandora's box or optimal shopping problem. So you have n distributions. The plan would be, our algorithm would be of the following kind. First, it would learn each individual distribution pretty well. So learn every single discrete distribution very accurately. We have to make it like, we have to quantify what exactly these terms mean. What do I mean by very accurately? I'll do that in a second. The plan of attack will be, first, we are going to learn each individual distribution very well. Then I'm going to combine all these distributions to give a new distribution. Like basically, I'll take the product distributions on this learned distribution. So each distribution di, you have d1, d2, d3. These are the original distributions. I'm going to learn some d1 hat, d2 hat, d3 hat. These are some learned ith distributions and distributions. And the new distribution I'm going to construct is basically d1 hat, product, d2 hat, product, d3 hat. So I've constructed an artificial product distribution by combining all of them. And that's what I'm going to feed to my offline optimization algorithm. Okay, but let's maybe make it more formal. So first of all, okay, what do I mean? So when we want to say that I want to learn a distribution very accurately, let's try to formalize it. And this is one very nice way of doing this is we have something called as the TV distance. So it's a very since many of you have not seen, I think this is like a very powerful idea, which you should take away from the talk, even if you didn't get much of the other things. So TV distance between two distributions, think of it as follows. You have two random variables. Maybe I think it would be better to think of an example. So suppose I give you two examples, two coins. One is a Bernoulli coin with probability P. Another is a Bernoulli coin with probability P plus epsilon. Okay, maybe you can think of P also being half. Like one is an unbiased coin with probability half. Another is an unbiased coin with probability half plus epsilon. So these are two distributions. They have nothing to do with each other. But a priori, these distributions seem like very close to each other. I mean, because it's literally like one is like exactly half, one is half plus epsilon. How would we formalize this, that these two coins or these two distributions are very close to each other? So the way to formalize this is via so-called coupling. It basically says, I'm going to define a distribution, another distribution over two-dimensional outputs, where the first output should be thought of as the output of the first coin, which has bias exactly half. The second output should be thought of as the output of the second coin, which has bias exactly half plus epsilon. So that individually, the marginals correspond to the two distributions, but they are more likely to be the same. So maybe to give you an example, like here. So because both these distributions I want to say are very close, I want to say like when the first one shows you a heads, the other one is also most likely to show you a head. When the first one shows you a tail, the other one is also very likely to show you a tail, up to an error of epsilon. But so more formally, the TV distance between any two distributions is defined as a coupling. So what's a coupling? Coupling is a distribution over pairs of random variables, where the first, like if you look at the projection of this two-dimensional random variable on the first random variable, this will correspond to the first distribution D. The projection of the second random variable will correspond to the second one. And in most cases, you want to say that both the random variables are the same. So the PV distance is precisely the probability that these two random variables are different. So if these random variables are always the same, then this TV distance will be 0. So yeah, please, maybe let's take some questions. Like this is. Yeah.
So in this case, if I have these two coins, I assume that they're not independent from each other, because otherwise, of course, I could have the case where the one with a lower probability shows me a 1 and the other one shows me a 0.
Yes. So in some sense, exactly like, so if I have two coins, like half and half plus epsilon, a priori, these coins have nothing to do with each other. Now we want to say like, imagine a world where these two coins are correlated with each other. We want to find out kind of the best possible correlation between these two coins, such that most likely they are identical. But the marginal distribution of each coin is as was originally promised. So in this particular case, when you have two coins like P and P plus epsilon, imagine a coupling where it's like 1, 1 with probability P, 0, 1 with probability epsilon, like these choices. My claim is now, the only case in which the two random variables are different is when you get like a 0, 1, which happens at most with epsilon probability. Now, if you see like the chance that you get like you get a 1 in the first coordinate, that's precisely P, because this or this one, like this happens with 1 P and this happens with 0. So the marginal probability of the first random variable is exactly P. The marginal probability of the second random variable, that the second random variable is a 1, is precisely P plus epsilon. This is as we wanted. So I've given you a coupling is basically a correlated distribution on these two random variables, such that the marginal of the first random variable, like first coordinate, is precisely the distribution of the first random variable. The second random variable is the second coordinate is the second random variable. Yeah. So in some sense, like it's thinking of it like you have two random variables. A priori, they didn't have anything to do with each other. I'm calling two distributions to be very close or very similar. if somehow I can map them to each other, such that in most situations they are the same. Okay, so it's kind of saying like the best possible mapping that I can come up with between two distributions, such that they are mostly the same. So precisely, it's the best possible mapping for which like the chance of them being not equal is small. Good. Yeah, and there are like some other equivalent definitions. It's also can be thought of like for discrete distributions. It's the L1 distance. Like look at every possible point in the support, look at the probability densities, and take the differences and sum it up. You have a question?
No.
Okay. Good. So why does this matter? Like, so this will allow us to quantify. Like again, going back to recall what our objective was. Our objective was that we have these n distributions, which are discrete, having support size at most k. The goal is we want to come up with like small number of samples and argue that we can learn a good algorithm. That was the original objective. Our idea is the following. We have these n distributions. We are going to learn each individual distribution very accurately. In particular, we'll ensure that we can learn a distribution up to a TV distance of epsilon or epsilon over n, some very small TV distance. So in some sense, I don't know the exact distribution, but after these many samples, we'll be able to argue that this distribution I know up to this 1 minus epsilon accuracy. In the sense like there exists some kind of a coupling between the two worlds, what I've learned distribution versus the actual distribution, such that like 99% of the times they are the same. With 1% chance, there's some error. So the plan of attack is I'm going to learn each individual distribution in small TV distance. And then I'm going to, like whatever I've learned, based on that, I'm going to construct a product distribution, feed it to my black box, and then argue that this is a good algorithm. Okay, so let's formalize this. So first claim is that if you have two distributions, D and D hat, if you come up with an optimal algorithm for D hat, like D hat is my algorithm for opt hat is my optimal algorithm for D hat, then the performance of this algorithm on the original distribution is going to be roughly the same as the optimum algorithm on the true distribution up to this TV distance. So, so the claim is basically what I'm saying is, if you have some original distribution versus you have some learned distribution, it suffices to optimize on the learned distribution. So if you can find me a good algorithm on the learned distribution, that will have a good performance on even the actual distribution up to this TV distance error. Okay, so up to this TV distance error, it suffices to come up with the optimum solution opt hat for D hat. Because if you run this opt hat on D, the actual distribution, the error performance will be comparable up to this TV distance. And this proof is literally like 2 lines, because you're running opt hat on D. You can replace D by D hat up to this TV distance, because up to this TV distance, D hat and D look the same. Here I've used the fact that my function is bounded by 1, 0 to 1. Once I have this, then opt hat is the optimum for D hat. So I can replace this opt hat by opt, because opt is some other potential algorithm, which is not tailored for D hat. And now I can again replace D hat by D by the TV distance bound. So that's the entire proof. So what this basically suggests is the following algorithm for our problem, for our stochastic optimization problem. We are going to first learn each DI separately to get a DI hat, which is going to be very good in TV distance. Turns out for this step, basically just take the empirical distribution, like a uniform distribution on the empirical samples. That would already suffice to learn each DI hat. Once you have these DI hats, I'm going to construct a product empirical distribution, which is basically for each of these DI hats, I'm going to take a product distribution over them, like independent on this. That's what I'm calling D hat. And then I'm going to just optimize for D hat. Send it to my offline optimization black box and get an algorithm. And via this lemma, the performance of this algorithm is going to be very good as long as the TV distance between these distributions are required. Does this make sense, or am I going too fast? question? Yeah, so even if you didn't get anything, like, I mean, so the main point here is like maybe some of the TV distance and all, like even if that machinery is getting like too technical. So the main high level takeaway message is just the following. You have n distributions. Learn each distribution separately. How would I learn each distribution? Here is where I'll use the fact that it's a discrete distribution. Turns out for discrete distributions, you can just look at the empirical distribution, like look at your samples. That gives you some kind of, and look at the uniform distribution on these samples. Turns out that's a very good estimate of each individual distribution because your original distribution is discrete. So just learn this each distribution. You can show that even in TV distance, it's good. Construct from this individual distributions, construct a product distribution, and then use the offline optimization algorithm. And you can argue that this works well. So the formal theorem is that as long as the number of samples is roughly like n square k over epsilon squared. So this n square factor can actually be even improved to n, but roughly like this, then you can get an additive epsilon approximation. So here k was, recall, the size of my support. And the proof is literally what I was saying. Like, first argue that for each distribution di, whatever you have learned, the empirical distribution, that's pretty good in TV distance. So it will give like a small TV distance epsilon prime as long as like the number of samples is something like k over epsilon prime squared. The second claim will be that the TV distance for product distribution, it just at most adds up. So if each individual distribution, each di I have learned up to an accuracy of epsilon prime, I would learn the original distribution, like the high dimensional n dimensional distribution, up to an accuracy of n times epsilon prime. So if I set epsilon prime to be something like epsilon over n, then I'll basically get this there. Any questions? Okay, good. So yeah, maybe I'll recap. And like these lemmas are not that difficult to prove. The first one, I guess I will discuss this in the exercise as one of the exercises. The proof is literally, again, like Chernoff bounds, and along with Cauchy-Schwarz. The second one is literally the following, that like if you recall the definition of coupling, you can define a coupling for this high dimensional world by basically taking the coupling for each individual distribution. That gives you a natural coupling for even the high dimensional world. And the high dimensional coupling will work as long as each individual coupling works. So basically, you can think of this as basically some kind of a union bound. So it's some kind of a union bound, hence you have this lemma too. So combining that gives you the other theorem. So let me skip this continuous part. So the main takeaways from this part of the talk was, okay, what is, first of all, the goal of data-driven stochastic optimization is we want to figure out what's the minimum number of samples needed to find the optimal algorithm up to an epsilon accuracy. The first algorithm approach we learned is via discretization. We said something like, as long as you're fine losing logarithmically in the number of potential algorithms, so the class of algorithms, the size of the class of algorithms, you can just apply simple Chernoff bounds, and that's already good. On the other hand, if you're not fine with that, but if you have like some discrete distributions or something else is going on, then if you have distributions which are discrete, then turns out you can learn each individual distribution very accurately in very small TV distance. Hence, you can just learn each individual distribution, construct their product distribution from these samples, and feed it into your black box and get a sample complexity of this kind, like which, yeah. And you can do like something more complicated than TV distance called Hellinger distance, which can shave off one of these n factors. But I mean, yeah, that's not required. The main takeaway here is that, yeah, for discrete distributions, you can learn them very accurately via samples. Turns out for continuous distribution, this approach does not work because you cannot hope to learn a continuous distribution in small TV distance. So next time we'll figure out some of these other ideas to capture them. Yeah, that's it. Thank you.